This conference will now be recorded.
Okay, so I see that instructions to install Keras, right? I just pushed it an hour back, so I just realized that I didn't share it. So in one of the folder, I think it should have been 28th of May, if I'm not wrong, 25th of May. Then I think in this folder, 25th of May, that folder I have pushed a PPT and the environment file. I just did it like an hour back. Okay, so please have a look at it and let me know, if you guys face some difficulties in installing the same. Okay, so I think we can get started. So we don't have much time to waste. So we need to kind of accelerate it. Okay, so let's get started. So giving you all a quick recap of what we have discussed yesterday. So just give me a minute. I'll open the PowerPoint. So we started with this thing, CNN models yesterday, right? So we started our discussion about something called as convolutional neural networks. So we understand that convolutional neural networks is a class of predictive model, which is going to probably solve two-dimensional data sets or three-dimensional data set problems, right? So I wouldn't even limit it to just three-dimensional or something. I think you can kind of design the same maths to work for even more dimensional data sets. But for now, let's just assume that CNN has been working on two-dimensional and three-dimensional data set, where the work of a CNN is basically to do something called as feature extraction, guys. I think we did see some examples, right? We did realize how is he doing feature extraction. So he's basically going to take up, let's say, an image or a video or let's say an audio, something of that particular sort, a 2D or a 3D data, and he's going to try and fetch only the most important features from that particular data set. Which means, let's say, for an example, if it's an image, right, he's going to fetch only the probable edges, or let's say the texture of that particular image there. So this convolutional neural networks, as I keep repeating, right, it's going to be very helpful whenever you want to find the relationship between, let's say, adjacent data, or when you want to understand the relationship, which is spatial or let's say temporal relationships here. So the CNN is more like a feature extractor, guys, which means, he cannot work as a predictive model. When you need a predictive model, you still need to use a multi-layer perceptron that we have already discussed. So can you see? This is like, after we discuss complete CNN, all the layers that goes into it, I'll tell you guys, this entire portion is going to be the work of a CNN model. That is, it can take up your image like this, then it's going to do all the feature extraction. It'll reduce it to a smaller image. But finally, you still need what is called as MLP, a multi-layer perceptron, or a simple deep learning model. Why? Because the CNN is only a feature extractor, guys. We did see examples, right? It is just a plain feature extractor. You can just extract the features for us. Once you've extracted the relevant features, now predicting whether it is X or O, you still need a multi-layer perceptron model here. Okay. So this is the point, guys. A CNN, please understand that it is more of just a feature extractor. He can help you extract the relevant features coming out of a predictive model, out of a data set, which can be pushed into a multi-layer perceptron model later on to learn, why do you think these features are probably giving us an X? Why do you think these features are probably giving us a 0? Right? So this is exactly what a CNN is doing, guys. And for doing the feature extraction work, like what we spoke yesterday, right? It needs something called as a filter, and it can do something called a 1D convolution or a 2D convolution like this. So one of the first foremost layers, or one of the workhorses of this entire convolutional neural network models would be the convolution layer. So like what we saw yesterday, right? We did go to Wikipedia, we did pull out certain filters, and then we were running it on the image that we had, right? So what was he doing? He was helping us understand the edge, or he was helping us probably sharpen the image, or probably kind of blur the image. So based on suitable kernels, there were suitable outputs that we did get. But now here what we're doing is we are creating a CNN model where the CNN model is saying, hey, don't worry, I will come up with a customized kernel for you. I'm going to come up with a customized weight matrix for you, where if you use this particular weight matrix and then convolve on the images, you will get the relevant features for your objective here. So what are we saying? If an example, if I want to do a face recognition, I need to understand where exactly our face is present in an image. So I need a certain filter which can go back and pull out that particular portion of the image alone. It can just go back and find the face portion alone. So for that reason, instead of using some traditional techniques and some traditional kernels or filters, here in a convolutional neural network model, we are saying, hey, for starting, I'll just assume some kernel values. I'll try to customize, train this particular kernel or the filter for your objective here. Do you want to do image processing? Do you want to do the face recognition, let's say for animals or something, right? So that's not something that's not available naturally. So don't worry. Let's go back and create this objective. Let's create a predictive model. I'll come up with the kernel which can go back and fetch the features of an animal's face probably. So the filter or the kernel here is actually being trained and created or customized by a convolutional layer that we see here. The same thing goes for any kind of image, okay? It can be for a single dimensional image, which means you have a single filter like this. Or if you have a three-dimensional image, then you can have one filter with 3 channels. Say for an example, you're given one image, okay? Assume it is RGB. So red color is one channel, green color is another channel, blue color is another channel. So I need to come up with one kernel. But the kernel's depth, right? Depth means what? The third dimension. The depth will keep increasing depending upon how many channels are available in the original input also. So if you have 3 channels RGB, the kernel will also have 3 filters here, or let's say 3 channels here. So now you can see this is kernel who's channel number 1, kernel's channel number 2, kernel's channel number 3 right now. Now what are they doing? They're basically going and convolving on the images. Whatever be the results that you're getting, he's just doing a simple addition and he's replacing it here, right? So the depth of the filter or the depth of the kernel that you see will also be dependent on the depth of the image that you see here. That's another point that I wanted to kind of add yesterday, okay? But otherwise, I think we've pretty much discussed in detail on how a convolution layer would work, right? It's basically striding over, in a particular fashion. We did discuss about the formulas on how it is giving you an output of a particular dimension, right? So we did discuss on the kernel size and all. So kernel size and all is something that you need to do it by a trial and error, guys. So, choose some kernel size, understand if the performance is good, else choose a bigger kernel size. So that's how you keep doing it. So this is exactly what a convolutional layer will typically do for us. So this is one of the important layer in a CNN module, something called as a convolution layer. Now over to another very important layer, guys. We have something called as pooling layer. So what do we have? We have a very important layer, something called pooling layer. So the pooling layer in a deep learning model is of 2 types. There's something called as a max pool layer, and then there is something called as an average pool layer. So there are 2 kinds of pooling operations we could do. One is something called as a max pool layer, and over to the second one we have something called as an average pool layer. So the pooling actually is a very simple operation, guys. I'll tell you. Once again, the reason for doing a pooling is to basically reduce the dimensions. That's all. So we're saying, hey, CNN is trying to, kind of come up with the most relevant features, right? Now, what I will do is I will in turn work on what a CNN layer is doing. Sorry, a convolution layer is working, and I will try to reduce the dimensions further. So the convolution layer will do something. He will extract the relevant features. Now you can add another convolution layer also if you want. Then you can probably add a pooling layer like max pool or average pool, which will work on the output of a convolution layer and it'll reduce the dimensions further. So what is the work of a pooling layer? It's very simple, guys. Unlike what you saw in convolution layer, there is no convolution operations and all happening here. So all we're going to do is we are going to take up a small filter. Okay, when I mean by a filter, it's just a small window. Example, a 2x2 window. What we will do is we'll just stride this window over this entire image. Say for an example, this is the 2x2 that you see. The four numbers are what? 0.33, minus 0.11, minus 0.11, and a positive 0.11. He'll take up the four numbers and he will find the max and he will replace it here, which becomes max pool. Or you can find the average of the four people and you can keep it here, which becomes your average pool. So you're taking up a particular filter size, guys, and you keep striding over. So next, what will you do? You'll probably replace it here. So you'll keep the filter probably here. So these are the four people selected. Who is the max out of this guy? 0.55. So I'll keep him here. Next, we'll move here. Who is the max right now? It's probably, let's say, so we moved here. We have moved here. I don't know why it is 1.0. Or did he move somewhere here? I don't know. Probably it's 1.0. Then probably he's moving out here. Then he says it's 0.77. So it is just going to move over this entire image like what we did in the convolution layer. And it's going to, consider a particular window of numbers and he'll find what is the max out of all those people and what is the average out of all of those people. That's all. Okay. So say for an example, guys, let's say we started this image. So what is this image? It's a 4D tensor. Why do I say it's a 4D tensor? Because it is nothing but the number of images cross the height of the image, the width of the image times the number of channels involved in the image. Say for an example, you can see it's 9x9 image. There's only a single image available and there is only one channel because it's a black and white or something. So it's only one channel right now. Now suppose say you're taking two filters. We are taking what? Two filters. The first filter is 3x3. The second filter will also be 3x3. There are two filters. There's a green color filter. There's an orange color filter. What is the green color filter doing? He is striding over this entire image and he's giving you a feature map. So he gives you what? He gives you a green color feature map. Then the orange guy will go and do his work on top of the image and he will give you a feature map which is orange in color that you guys can see here. So this is the output of what? This is the output of a convolution layer right now. So what is the filter size? You can see 3x3. There is what? Only one single channel because the number of images is having one channel only, right? So the images are basically having one channel only. And there are two filters that we have here. One filter green, another filter orange. That's why the result you can see, it's 7,7. It has reduced in size. There are two outputs because you have used two filters right now. Once again, you can do another convolution on top of this guy. Now you're saying, hey boss, the image right now is having two channels. So what is he having? He is having two channels right now. What did we just discuss a minute ago? We said, hey, if an image is having one channel, the kernel will also have one channel. If the image is having two channels, the kernel will also have two channels only. If it's having three channels, the kernel will also have three channels right now. Hence, go back and see here, guys. If this is an image that we have who is having two channels, the filter should also have two channels, isn't it? That is why you can see there is a green color filter with two channels. There is an orange color filter also with two channels. So what is happening? There's a green color filter who's also having two channels. There's an orange color filter who's also having two channels. So we are saying, hey boss, the filter should be 3x3 size, but it should have two channels. Why? Because there are images with two channels with me. And there are two number of filters I've chosen right now. One green filter and an orange filter. What will happen? Let's just go back here. So let's assume we have only a 2-channel image. Let me just delete this portion, right? So what will you have? So the feature map is taken, the second feature map is taken. In the filter, you have the first channel, the second channel, they will produce one output for you. Next, another filters first channel, another filters second channel, they will come and work on this guy. They will produce another output for you. So just go back and check, you can see. So the green color guy, the 2 channels, right? This guy will work on him. This guy will work on him. They will produce one output, which is the green output you can see. This orange's first channel will work on him. The orange's second channel will work on him. They will produce one single output, which is this one. So the resultant size right now has become 5, 5, 2 channels as output right now. Right? So let's go over again. A single channel. That's why the filter is also having single channel. But there are 2 filters, one green filter, one orange filter. Green filter works, gives you an output. Orange filter works, gives you an output. Next, this output will be used in the next convolution layer. So this is a 2-channel image. So the kernel should be 2-channel. That is why green color first channel, green color second channel, orange color first channel, orange color second channel. So one filter will produce one output, you can see here. Another filter will produce another output. That's why from 9, 9 it became 7, 7. Further from 7, 7 it became 5, 5. So you're reducing the dimensions of your image, pretty, what I would say is aggressively. You're reducing it, pretty fast here. So from 9, 9 it became 5, 5. Now what you're doing is you're feeling, okay, instead of doing a convolution, making my model more complex, right? Can we make it a little bit more simple? Feature extraction, can we kind of make it a little bit more simpler? That's why we are going to add a pooling layer right now. Now we are saying, hey, let's take up a small filter. Let's just try it over this entire image. And then that window of numbers that he's choosing, let's go back and calculate what is a max, or let's go back and calculate what is the average. Let us use that particular number. We will end up with what? Features. So you can see in this pooling layer, we have taken up a filter, right? I mean, it's like 3 filters, by the way. I think it's 3 filters. It should be 3. Not like 3 filters. Sorry. I'm making a mistake. Sorry. It's basically the output coming from previous case, right? So 7, 7, 3 channels. Yeah. Now all you're doing is you're taking up the filter, striding over this guy, and you're reducing it small. So it becomes 4, 4 with 3 channels. Okay. So there's no concept of as such filter. It's just a window of numbers. You're taking a small window and then you're just sliding over this guy. Then you're finding what is the average or the max. That's it. Okay. So this is called as the pooling layer, guys, where the pooling is actually another kind of an operation which can help you find the most relevant features in the image here. Let's go back and check an example. So I think we'll come down here. So let's just import all the necessary things we need. So let's import the image. Meanwhile, let me also import NumPy, pandas, etc. So let's come down. Okay. So the pooling layers are here. So what we're going to do is we are saying from keras.layers, please import average pool D. From keras.layers, please import max pool D. Let's hit Control Enter. He is imported pooling layer, 2D pooling layer, average type, pooling 2D layer, max type. So max pool, average pool, both the layers are now imported. Now what we're going to do is we are going to reshape our image. So what is the image's shape right now? 512, 512. We don't need 2D, we need 4D because deep learning models will understand only 4D tensors. So we are saying image is equal to image dot reshape. It is 1, 512, 512, 1. So you made it as what? You have made it as a 4D tensor right now. You're saying, hey, it's a single image who is having 512 height and 512 width, and there's only one single channel here. because it's a black and white image. Now let us go. We'll say, hey, model is equal to sequential. Model.add. Let's add a max pool D. The size of the filters are going to be 5 by 5. So 25 numbers will be taken and he'll find what is the max out of those, right? Input shape is 512, 512, 1. You're just compiling it. Okay. So we didn't import sequential. Okay. Okay. So now what we will do is, guys, we'll go and say, hey, model, can you just please predict? Can you just do the feed forward propagate? So what are we asking him to do? We are asking him to do the feed forward propagate only right now. No back propagation. Back propagation starts only when you say model.fit. We are saying whatever be the weights that you've kind of assumed right now. I don't think there's going to be any model weights. So let's just ask if there are any weights. There's no weights actually speaking because this is a max pulley. You can see there are no weights, right? It's just a window of numbers he's going to concentrate on. There are no weights as such. So using the word as saying feed forward propagate also is right now wrong because you're not having any weights. You're not multiplying and computing any output. Anyways, so let's call it as feed forward propagate still, even though we are wrong. Control enter. You can see right now the output is 102, 102. Let's fetch only the image. Let's go back and ask him to plot the image. Can you guys see? Right now he has reduced the size of the original image from 512 to 512 to 102 into 102. Right? So the original image was little, what I would say is bigger. You can see this was the original image, 512 by 512. So whatever be the information that's available here, he was able to retain it as it is here, right? So when you do a max pull D, guys, what you will see is, you will see what I would say is a little bit more sharper image. Do you call this a sharp? Yes, I think I would call it a sharp. It's more of a sharper image. But if you're probably doing an average pull D, look at this case. We're going to do an average pull D right now. Okay. So final prediction, I'll go and make a copy of this guy here. So this is going to be an average pool's result. The result of an average pool will be much more smoother here. Can you see? Compare the two outputs. Here it's a little bit more sharper. I'm not very sure if that's the right word, but yes, I can see that it's a little bit more distorted or probably even a little sharper. But in this case, you can see it's much more smoother in nature, right? So compared to max pool, the average pool is kind of, smoothing it out. So you see it a little bit more blurry, but here it's probably a little bit more sharper or, distorted. What will be the right keyword, right? So I would say, you need to mix up, use max pool D, use average pool D, try to use everything, all kinds of varieties possible. Don't take a plateau, don't keep it very, what I would say is simple. Try to give a lot of varieties. Use something like max pull D, use something like average pull D. Now these guys will basically try to reduce the dimensions of your image here. Now these are the two very, very important layers, or I would say the only layers of your CNN module that you need to understand, which is actually going to do the feature extraction for us. That's it. So can you see? There's like all of it together. So he's saying, let us add a convolution layer. You can keep an activation function like reloop. We've already discussed it. He's saying add another convolution layer, add another reloop on top of it. Then he's saying you can do some pooling layer. Then he's saying you can do some convolution. He's adding a reloop once again. He's doing a pooling once again. I mean, just a variety of layers. He's just using a variety of layers here. So probably if you started off with an image which was 512 cross 512, now it might probably end to 128 cross 128. After all these series of operations, it might become 128 cross 128. Then what we will do is, guys, then we will say, okay, let us take up this particular image and flatten it out. So the point is, guys, we are actually going to create a multi-layer perceptron only by the end of the day. So if you all remember, one of our first discussions on why we are using CNN is because I told you, right? When I have an image like this, probably let's say 512 cross 512, in a multi-layer perceptron model, you should have probably flattened out this entire image, right? So you will have what? Numbers starting from 0 till 512 square. You will have so much of data, right? Then you will say, hey, this is the target, saying that, probably it is X, then it is O. Then similarly, if there is another image, which was 512 by 512, what would you do? You will flatten that entire image, starting from 0, goes up to 512 square set of numbers. Then you'll say, this is my target, it was X or O. But the only problem is, guys, if you see, the number of dimensions are literally too much, right? The number of dimensions are what? It's literally too much. 512 squares number of pixels, I don't think so. I don't think, multi-layer perceptron models can handle. That is why now what we are doing is we are saying, let us use a CNN plus an MLP combination. What is the CNN saying? He's saying, instead of using an MLP as it is, why don't you use the CNN plus MLP combination? So if you're going to use the convolution neural network, I can help you condense the relevant information available in the image to probably a very small image, let's say something like 28 by 28. Even this image, I can just convert it as 28 by 28. Now what are you doing? You're flattening it. You will only have only 28 square number of features. Here also you will have only 28 square number of features. So the difference is, instead of having a big set of data like this, you're condensing all the information available in the big set to a small set of data like this. You're making it pretty small. Then you'll say, hey, this is my target. I want you to create a multi-layer perceptron. Then you can create a multi-layer perceptron here. So please understand, guys, CNN is not a predictive model. It's just a feature extractor. So all he's going to do is he's saying, hey, images which is of big dimensions is something multi-layer perceptron model may not be able to handle. So don't worry, I'll take up the pain and I will try to reduce the dimensions for you. He's saying what? I can help you try reducing the dimensions for you. I can make it pretty small, like 28 by 28, which you can later flatten it out and send it to the multi-layer perceptron model as you always do. So what are we saying? We are saying multi-layer perceptron models cannot handle the images directly because of the big dimensions. Hence, what we will do is we'll try to reduce the dimensions using a CNN model, and then we can push it to a MLP. Which means, guys, what we need to do here ultimately is, after reducing the dimensions, you need to introduce a layer called as a flattened layer. So what are we doing? If it has become 512 by 512, you're reducing the size down to probably 28 by 28 using a lot of layers involved in the CNN model. Then you're just going to flatten it out. You're going to make it as a one-dimensional vector like this. So these guys will be your X. Then you will have your original Y. Let a multi-layer perceptron do its work on this data here. That's all. So what are you going to do right now? You're going to leave it to a multi-layer perceptron to do its work of predicting. So what is this X? What is this Y? Why are they kind of related together? You're going to leave it to the multi-layer perceptron to do this particular job for us. So please understand, guys, that CNN is basically nothing but a feature extractor. He can just extract the relevant features for you and give it probably to a multi-layer perceptron model. So big images is something that MLPs may not be able to handle. That's why we are saying, let's leave it to a CNN who can reduce it to a smaller image by keeping all the relevant information, and then let us leave it to a MLP model to do his regular job, like always he does. Okay. So please understand, guys, CNN, a mere feature extractor, doesn't do any kind of a predictive work, right? The predictive part is typically done by the multi-layer perceptron models that we see here. Okay. So let me give you all a good example. So let's go back to our MNIST problem itself that we have already discussed. Okay. So look at this case, guys. So I'm importing the train.csv and the test.csv. And look at the head of this particular data set. Okay. So what do we have? The digit recognizer data set that we have already discussed. All of us are familiar with. The first column is the label column, or otherwise your target. And these are all the predictors, the different pixels you have, right? So these are all the predictors. This is your first sample. He's having a label of 1. Somebody has written a 1. These are all the predictors, all the pixels you have, 784 pixels. So now you can see what I will probably do is I'll take up one of the image and I will visualize it for you all. You can see it's 8. So it's what? 28 by 28. So there are 784 pixels available with us. So every sample is going to have a target and 784 predictors. So this is the other sample. This is the target, 784 predictors. Another sample, 784 predictors. So what we will do right now is, guys, so we're going to convert this, we're going to basically create a multi-layer perceptron model here to do the digit recognizer job. So let's try to do that. So see here, we need to flatten the images, right? Every image, right? So actually speaking, it is kind of flattened. So you can see here. So now what we have is, we have what? The 42,000 images that we had and the 784 pixels for each and every person. Actually, this step is not necessary because it's already in that format. Okay. It's having the 42,000 samples and the 784 pixels, but I'm just making it as an array. Here it's in the form of a data frame. Here we are making it as an array. So what do we have right now? We have all the 42,000 samples and we have the 784 pixels, which are basically the predictors. So what we will do is, guys, we are basically going to normalize the data by dividing it by 255. I'll come back on the point of normalizing in a minute, why we are doing it. So if you try to relate it to the clustering example. So what did we do? We did Z transformation, right? X minus mu by sigma. Similarly here, this is one kind of normalization. When you divide it by 255, it will become numbers running from 0 to 1. Okay. So I'll come back in a minute. I'll discuss it a little bit more in detail. So we are just dividing by 255 so that everybody runs between 0 to 1 only, so that scales do not cause a problem for us. You don't have to have numbers running from 0 to 255. Rather, you will have numbers running from 0 to 1 right now. So what do we have? We have the target. We'll convert it as the dummy encoding that we've spoken about. So now what we will have, instead of a single target column, we will have several target columns. So this is a sample which had digit 1, right? Hence you can see 1 here. Other areas it's all 0. This was one sample which was actually showing a digit 0. That's why here it is 1. Other cases it's all 0. So dummy encoding, we have already spoken about it. So the target, you can see we are doing a dummy encoding and we are preparing the target. So a single target column has become 10 target columns right now. So go back and import sequential, import dense, import Adam, RMS prop, etc. Let's hit Control Enter. We are saying model is equal to sequential. Model.add, we are adding the first layer. We are adding 512 perceptrons. Second layer, 256 perceptrons. You can add more and more layers also if you want. This is the last layer that we have. In the last layer, we are having 10 perceptrons. Any reason why? Why we are having 10 perceptrons? I think it's been completely one way. Let me ask you a couple of questions. Why are there 10 perceptrons? Exactly. So there are 10 classes we need to predict. Why is there a softmax and not a sigmoid? Yes, so why is it a softmax? Because it's always a single digit, right? It's a mutually exclusive problem. Very good answer, Manohar. Thank you. So it's an exclusive problem. That's why we're keeping it as softmax here. If it is softmax, you need to keep something called categorical cross entropy. I'm sorry, not because it's softmax. So if it is binary problem, guys, you need to keep binary cross entropy. If it is more than two classes, you need to use categorical cross entropy. Okay. So the difference is one is called plain log loss, the second one is called multiple log loss. That's all. You have binary classes, now you have multiple classes. That's all. Binary cross entropy and categorical cross entropy. So now the RMS prop optimizer we are using, accuracy is what we want to see. Okay, let's hit, I don't need to have model. Let's hit control enter. So we have the model. So let's go back and look at the summary of this guy. So he's saying what? Hey, the output is going to be 512 outputs. Why? Because you have 512 perceptrons. How many parameters? He's saying 4,01,920. What is the reason? Because we have 784 pixels times 512 perceptrons plus we have 512 biases. So the number of weights would be 784 into 512 plus 512. That's why it is 401920. So these many number of parameters are required. Why is this guy 1,31,328? Because 512 perceptrons here and 256 perceptrons here have to get connected. That's why the matrix is going to be 512 cross 256 plus the 256 perceptron here needs 256 biases. Control enter, 1,31,328. Over to the last case, it is 256 cross 10 plus 10 biases that you need. That's why you can see it is 2570. So these are the number of outputs you're going to get. These are the number of parameters. He's going to go back and estimate these number of parameters. Now let's ask him to train the model. He's actually started training. So we are giving 10 epochs, batch size is 128. We are asking him to keep a validation split of 70-30. So the first 70% of the data set will be used in training, 30% of it will be used by testing. So you can see here both the train and the test accuracies losses. Okay, so the 10 box is done. So the training loss is 0.00. It's a very good number. I would say it's an overfit number. In fact, accuracy is 99%, is good. For the testing data set, loss is 0.12, which is okay. We can live with it. Accuracy is 97%. Looks good. So this is exactly what the multi-layer perceptron model is giving us as a result. Right? So this is the output coming from a multi-layer perceptron. In fact, you can go back and visualize it and all if you want. So we can go back and ask for the history. He'll give you all the answers here. So we'll probably ask for the accuracies. Okay, so what accuracies is he giving us? Okay, it's train accuracy. So this is train accuracy is giving us. Similarly, you can also take up validations accuracy. Validation ACC is here, right? So we can go and say PLT dot plot this accuracy and the validation accuracy also dot plot this. The moment you hit control enter, you can see this is how the accuracy is working. How about the loss? For loss also you can do the same thing. Let's say this guy is loss and here we'll say validation loss. So the loss keeps reducing, right? Then after a particular point, it has become kind of stagnant. Here the loss is reducing, but later on it's probably increasing a little bit. Right? So the orange one is validation loss, blue one is training loss. Your blue one is training accuracy, orange one is validation accuracy. So this is how the training has happened. So you can get the training report also like this. Just say h.history. Now this is exactly what the MLP model has done using 784 pixels or 784 predictors. So we did not use any CNN. We just used the same MNIST dataset and we were trying to use it on the multi-layer perceptron model. These are the results we are getting. Now what we will do is we'll say, I think 784 pixels is a pretty big number. Why don't we use a convolution neural network and reduce the dimensions? Okay, let's do that. So let's just come all the way down. Now you guys can see here, we need the data set as two-dimensional, right? Because we don't need to keep it as one-dimensional. It has to be two-dimensional because you're doing 2D convolution. That is why we are reshaping it as -1. -1 means as many number of images you have, where each image will be 28 by 28 with a single channel. Let's hit Control Enter. Let's go back and see. So 42,000 images, where it is 28 by 28 size with a single channel here. A single channel, 28 by 28, 42,000 samples. We are going to import all the necessary things, right? Now we will go back and say, hey, model is equal to sequential, add a 2D convolution. Can you all tell me what is this 32? What is the meaning of this 32? So what is that 32 there? What happened, guys? I think it's a simple question. It's the number of filters, isn't it? Yesterday, while we were doing convolution, we always said, hey, it's going to be the number of filters. So we kept it as 1 here, which means 1 filter. We kept it as 2, which means 2 filters. Is the number of filters that we are talking about here, right? So we are taking up 32 filters, and the size of this guy is going to be 3 by 3. I think we haven't specified the stride. The stride by default should be 1, 1. We are just telling him the input shape is 28, 28, 1. So it's going to have height and width of 28 and 1 single channel. Then what are we doing? We are adding a max pool D layer where the pool size is going to be 2 by 2, which means I'll take 4 numbers at one time and I will do the max of those people. Suppose that I'll do an activation, which is ReLU activation. And once the reduction is all done, I will flatten it out is exactly what he's saying. So he's saying, hey, originally you had what? For every 42,000 samples, you had 784 predictor. For each 42,000 sample, you had 784 predictors. Now he's saying, using all the convolution operations and all, I'll try to reduce the number of predictors for you. Then I will flatten it out. So let's just look at this portion of it. Okay, I'll just hit Control Enter. So convolution 2D is not defined because we haven't imported it yet. So let's go to the top. Okay, I've imported it. So now let's come to the bottom. So now let's hit Control Enter. Let's look at the summary of it. So he's saying, what? You gave me a 28 by 28 image. I've used 32 filters, and each of the filter are reducing the image size to 26 by 26. Right? So I have 32 outputs. Why? Because we have 32 filters. Each of the filter will produce 26 by 26 outputs. Then what did you keep? You kept a max pool D. So the pooling will happen on all the 32 channels you have. That's why there are 32 outputs, and each output is going to be 13, 13 size. Then you're doing an activation which will produce the same output. Now flatten it out. You have 5408 number of features. I think in this case it has got bigger, but I'm just telling you. So here it's actually pretty simple. We just had 28, 28. It's already very small. So just think of some other case where it's actually much more bigger. Okay. So here 5408, I'm pretty sure, yes, it's bigger than what we were assuming. So we can probably do something else. We can probably keep the filter size much more bigger if you want. So we can keep it as 10 by 10. Your pool size, we can keep it as 5 by 5. Now, if you probably do it, you'll end up with a much more smaller data, 288, right? But anyways, in this case, we'll keep it as it is so that performance doesn't take a hit. Okay. So let's get the output. So 32 outputs, 26 by 26, 32 outputs, where you're finding max pool became 13 by 13. The same 13 by 13, 32 was pushed into activation. Flatten it out to give you 5408. So after flattening it out, now what are you doing? You're creating your multi-layer perceptron. So one layer with 128 perceptrons, another last layer with 10 perceptrons, activation is softmax. Same categorical cross entropy, RMS prop accuracy. Let's hit control enter. Now let's go back and ask him to fit the predictive model. So he has started learning. So he's training each and every weight that you saw here, 32 filters that you had, right? Each and every filter is getting trained here. And why is it 320 here? The number of parameters are 320. Can somebody tell me why it is 320? So why do you say that there are 320 parameters here? Can somebody tell me? What happened, guys? Yes, why is there 320 parameters there? And by the way, so here you can see we just ran 2 epochs. In the second epoch itself, you've got 97% accuracy, whatever you wanted. Go back and check here in the second epochs in MLP, what did you get? The second epoch, you just got 95 or something, right? Here in the second epoch itself, you've got 97% accuracy on the test. So we can just go for an additional epoch also if you want. So I can just hit control enter as it is, it will resume again if I'm not wrong. So it can give you more accuracy right now when you go for a couple of more extra epochs, right? So why do you think there is 320 parameters here? I think the answer is pretty simple again. So we have what? Each filter which is 3 by 3 size. So 3 into 3, 9 weights. And we have 32 filters like this. Go to calculator. So 9 into 32, you get an answer 288, right? Plus you'll have 32 biases. That's why there are 320. For each, for each filter that you see, there is going to be one bias, right? Go back and look at the PPT. Here you can see there's one single bias we keep, right? So for each filter, there's going to be one bias. That's why plus 32, which gave you 320 parameters here. Here and all, there's no parameters at all. What is the reason? Because here it's just maxing. So you're just, taking a particular piece of it and then you're finding what is a max. Here you're doing activation. Here you're flattening it. That's why there are no parameters. Here there is parameters, 128 parameters he's saying. Sorry, not 120 parameters, 6,92,352. Why is there so many? Because in the previous case, there are going to be 5408 outputs into 128 here, plus the 128 biases. That's going to give you 6,92,352 parameters to estimate. Why is it 12,290 here? Because you have 128 perceptrons, another 10 perceptrons here. These many weights are required plus 10 biases. That's why 1290. And now what has happened is you were able to train this predictive model. We could have saved the result somewhere here. So let me just do it again. So let's probably run it for 3 epochs. Let's hit control enter. Then we can just go back and plot what was the accuracies. Guys, are you all following till here? Yes or no? Every line by line, why is there so many parameters? Do you follow the calculations and all? Yep. Nizam, Jishbu, Manohar, Sanjay, Savik. Are we all on the same page, following the calculations? Okay, let's plot it. Let's plot it. So you can see this is how they are working. Right, this is 2 epochs. That's why probably 3 epochs, right? So first epoch, second epoch, third epoch probably. So this is how the performance is working with a CNN and an MLP combination here. So you're not using a only multi-layer perceptron. You're using a CNN plus multi-layer perceptron combination, which probably gives you a very, very good answer just to the second or the third epoch itself. Right? So this is exactly what is called as a convolutional neural network model, guys. I think we've pretty much discussed everything in detail, every smaller piece of it. So what do you mean by convolution layer? What is convolution operation? How are the weights getting recognized? How many filters? How is the output getting computed? What do you mean by pooling layers? So how can I use them to create a predictive model? I think we've pretty much discussed everything here. Right? Yes. Now tell me guys, any questions till here? Did you all follow this concepts, all concepts starting from our multi-layer perceptron till CNN? Any questions you have for me? Did you guys follow it completely? The last 2 weeks completely starting from MLP till this CNN point? Are we all on the same page? Yeah? Any questions till here guys? So starting from, how to create a MLP, what do you mean by perceptron? What do you mean by layer? What do you mean by activation function? What are the different algorithms available to solve it? What is CNN model? In CNN model, what are the small pieces? Yeah? Okay. Okay. So I think with this, then we are probably done with our MLP and CNN models. Okay, so the 2 topics are done. So what we can probably do next is, there is recurrent neural networks, which we'll probably take it up in the next class. Okay, so let's have a small, um, what I would say is a break from this deep learning things. Probably recurrent neural networks we can start off in the next class. Okay, so let's do something. So let's take a 5 minutes break, guys. Okay, and then let's be back. We'll probably take up SVM model, support vector machines. I think we should be able to condense it in 2 hours. So let's probably take up support vector machines models, and we can discuss it for the next half of the session. Okay. So let's take a 5-minute break, which means let's be back by 6:10. Then post this, we'll start off with our support vector machines model, because support vector machines is once again very similar to all of these things, to the MLP we have discussed. So I feel support vector machine should be a good thing to start off with. Okay, it's very, very similar to your MLP. So let's, touch base on that particular model next. Yeah, cool. Let's take a 5-minute break, guys.
This conference will now be recorded.
Okay. So, so what I told you all is like, right, so in the first half of the session, let's take a small detour from our RNN model. Okay, so I think you need some time in digesting a couple of things, your MLP, your CNN, etc. So let's take a small detour. Let's take a much more, I would say, a sort of a lighter topic. Okay, something like support vector machine. So support vector machines is yet another class of predictive models that we need to understand. Okay, so I'm pretty sure by this particular point, most of you would have got literally kind of fed up in the sense, hey, how many more models are we going to probably learn? It typically happens. So exactly when I start, support vector machines or something, this question is always asked. Why do you think are we discussing so many predictive models? So the answer to the question is very simple. It's just that, if one model can literally answer any question you ask, then there won't be a reason on why we are discussing all these models here. So you have an answer. If there is one model which is going to answer literally every question you ask, right? We won't even have to go back and discuss all other predictive models here. Unfortunately, it's not happening. So there's not a single predictive model which can answer your questions. So why did we discuss something like logistic regression? The reason why we're discussing logistic regression or linear regression is because basically it's a statistical model, which means any output that the model is going to give me, I can relate it to the business. I can go back and explain it to my business partners. So I can tell them, hey, I'm getting a coefficient something like this. The reason is because so and so we have tried and tested. So we're going to see this kind of an effect in near future. You're able to quantify and give them an answer, right? So it's something that you can go back and relate it to the business. You can speak with your partners and say, hey, this is what it is expected. This is how the model is telling us. So let's take something like decision tree. Why would you create decision tree? You will create decision trees when you start, when you start, what I would say is, probably wanting, when you want probably some kind of business rules which can be applied. Say for an example, if you're probably an underwriting company, okay, you're going to do some underwriting and all. So underwriters basically work with some rules at the back end. So how do I come up with certain rules that the underwriters can probably follow? You may need what is called as a decision tree model, because decision tree model is giving you rules only, isn't it? He's saying, hey, if this condition satisfies, if that condition satisfied, the third condition satisfies, then I think, okay, the accident that has happened is completely natural. So let's go back and action is claimed, right? So in cases like this, you may want to have something like rules which you can pass on to people. That's why we create decision tree models. And why did we discuss backing boosting and all? Because we said, hey, single decision tree may not be good. Let's combine a lot of decision trees. Why did we discuss neural network? We said it's one of the best models that you can ever create. The support vector machines we're going to discuss is also one of its kind. We call this guy once again as a off-the-shelf predictive model. Why? Because even though he may share a lot of formulas, methodologies, etc., very similar to that guy, there's still a lot of uniqueness left off with him. So the formulas could be the same, or some kind of optimizations and all could probably be same. He might share it with MLP, but I would say there is a lot of other uniqueness in support vector machines compared to other models. So typically what happens is, guys, we create something called ensemble of models. What do you mean by ensemble of models? Create a lot of predictive models, right? In those cases, we know this point that the different predictive models that we're going to create should have a lot of diversity, right? So we disqualified bagging and we went on to random forest. Why? Because we said, hey, in bagging, there is still scope of models getting duplicated. That's why we did variable, selection methods using certain methodologies, and we came up with random forest. Then what did we do? We said, okay, let's probably try to, make every model better over the previous one. Thereby, we'll still create a lot more uniqueness. That became something called boosting. So whenever you're trying to do an ensemble, guys, you want the models to be more and more unique. You don't want them to be duplicates. You want them to be unique. That is why there are different class of models. You may probably want to create one model which is random forest, one model which is neural network, one model which is support vector machine. Get the results from all the people and you can probably average it out. Different kinds of models, a logistic regression, a neural network, an SVM. Create different models, get predictions from all the models, then average it out. So that is yet another reason on why do we have to understand different predictive models here. Support vector machines, a very, very important class of model, guys. Okay, we call this as, once again, another off-the-shelf kind of a predictive model. So early in the 1980s and 1990s, when neural network models were not possible to be created, support vector machines were the best in class. They gave the best results. Boosting and all came very recently. Okay, boosting was like, let's say 3-4 years back, that's all. But support vector machines, neural network, their max is all available since the 80s and 90s, or even before that, if I'm not wrong. But support vector machines was widely implemented. It's easy to implement compared to neural network. So support vector machines were the default models you can see many people would have used. Go back to any ML research paper, you'll be able to see people using support vector machines very often, rather than neural network, which is more popular today. So the work of a support vector machine, guys, is very simple. He's basically going to create what is called as a hyperplane, which can divide the different classes of data. By the way, SVM once again can do both classification and regression. You call it as SVC, which means support vector classifier, or you call it as SVR, which means support vector regressor. But the idea is actually same. 95%, they're going to be very similar, okay? So if we discuss classification, it means you've understood regression also. So let's take up the example of a classification, guys. So what a support vector machine is actually doing is, it is just creating a decision boundary which can separate the different classes of data here. Okay, so just give me 1 second, guys. Hope it's okay. That's fine. Okay, so what is the support vector machine doing? It's basically creating what is called as a hyperplane, which can separate the two classes for us pretty far away. Before understanding the support vector machine, let's go back to logistic regression, guys. Okay, because you'll see a lot of similarity between logistic regression and the support vector machine's intuition. Let's take up the logistic regression. In logistic regression, what do? We have something called as a sigmoid function, which will give you probability, right? So what is the formula? Probability is equal to exponential of beta naught plus beta 1 times of x divided by 1 plus exponential of the same. So this is probability function, or also called as a sigmoid function, right? So the sigmoid function here, this guy, will give us what is called as probability. How do we estimate the beta naught and beta 1? We are basically going to use something called as a log loss. So we are saying, hey, take up the true value, multiply it with the log of probability plus 1 minus yi times log of 1 minus probability. This will give you something called as loss, which needs to keep reducing as much as possible. So we will say what? Hey, take up the probability, find the log of probability, multiply it with the true value. This will give you what is called as the loss for us, what is called as a log loss. So what is this curve? If the target is 0 and if the probability keeps increasing here on the x-axis, you can see the loss will also increase. For a target which is equal to 1, if the probability is increasing, the loss will keep decreasing. That is lesser probability for target of 0 and higher probability for target of 1 is good things to do. Higher probability for a target of 0 and lower probability for a target of 1 is bad things. That's why you have a higher loss here. So what are we saying, guys? We are saying, hey, you can keep a benchmark like this. You can keep a benchmark like 50% and say, if it's above 50, let's keep it as 1. Below 50, let's keep it as 0. You could have done it. That is what accuracy wants. He just needs ones and zeros. But what is the loss saying? The loss is saying, hey, for a target value of 1, the prediction that we are coming up with, right? That is your parameter into your input should be as big as much as possible and for a target value which is equal to 0, the predicted probability that you're coming up with should be as small as much as possible. So here we are saying for a target value which is equal to 1, we want the probability to be as big as much as possible. The bigger and bigger it is, the more happier we are. And here we are saying for a target value of 0, the more lesser and lesser it is, the more happier we are. So what are we saying? We're saying the more the probability for a target value of 1 and lesser the probability for a target value of 0, the more interested we are at this particular results is exactly what we are saying, right? Now taking the same kind of an inspiration, guys, that's exactly what even an SEM is going to do. What an SEM is saying is, the SEM says, hey, I can help you create a support vector machine. That is, sorry, a hyperplane. So what is the support vector machine saying? He's saying I can help you basically create a hyperplane. So this will be like a dividing plane or a hyperplane. So what I will do is, I will basically push some people on the right hand side and some people on the left hand side and make sure that this class of data is very, very far away from the hyperplane, and also this class of data is very, very far away from the hyperplane. Or otherwise you're saying, if this is going to be the hyperplane, if let's say for an example, guys, you have a data point A and here you have a data point B, okay? So here also we are predicting it is class 2. Here also we are predicting it is class 2. Now I'll ask a question to you all. Tell me, are you more confident with your prediction that A is more of a class 2, or do you think B is more of a class 2? Which one are you more confident? Do you say that the point A is more of a class 2 member, or do you guys think B is more of a class 2 member? Which one do you think is having a higher chances of being class 2? Exactly, it's going to be A, right? Why? Because he is very, very far away from class 1. It's very far away. He's having a lot of uniqueness, so he's very far away. So from the hyperplane, he's too far away compared to the B, who's not very far away. So I'm more confident in predicting that A belongs to class 2, and rather not much confident that B belongs to class 2 because it's more closer towards the hyperplane. The same thing goes even for this case. Let's say I assume one data point here. Let's call this as A. Let's call this as B. I'm more confident that B is more of class 1 compared to A being class 1 because he's much more far away. So all we are doing is, guys, we are saying, I want to create a hyperplane which will divide my data set, saying people on the right hand side is one class and people on the right hand side, sorry, left hand side is of another class. That's good. But I need to make sure that the two classes of data are very, very far away from my hyperplane. Why? Because I could have created a hyperplane something like this also. But what do you see? This green is very close to him. The red is also very close to him. Or I could have created a straight line like this. Once again, this red is very close to him. This green is very close to him. There are so many hyperplanes possible. I can create as many number of hyperplanes as I want. But which is the hyperplane which is best in nature? The best hyperplane is somebody who divides the two classes of data with a maximum distance as much as possible. So the two classes of data should be as far as much as possible. The more they are far away, the better off is my predictions. I'm more confident that they are class 1 and class 2. I don't want to create a hyperplane looking something like this because they're more closer towards the classes. Or I don't want a hyperplane something like this because they're more closer towards these data points. I want the blue color one because it's much more far away from the extreme data points of the respective classes that you see. So what are we doing, guys? We are creating something called as a support vector machine model, which is otherwise nothing but a plain hyperplane The intuition behind creating a hyperplane is that when you take up a logistic regression model, what is a logistic regression model saying? He's saying, I am computing beta naught plus beta 1 times of x, which is otherwise theta transpose times of x. Okay. Now, what are we saying? We are saying if the target value is 0, keep the theta transpose x to be a negative number. Probably I'll say very, very big negative number, or it should be a very small number. It should be a negative number. Only then when I apply it to the probability function, I will get probabilities which are all very low. Why? Because for a target value of 0, I want probabilities to be lower. Similarly, guys, for a target value of 1, we want the theta transpose x to be a very, very, very big positive number. Why do we want it to be a very, very, very big positive number? Because only when I apply it to a probability function, I'll get a probability answer which is very, very big here. Because I want for target value of 1 higher probabilities. So the beta naught plus beta 1 times of x should be a very big negative number. Only then I'll get a lesser probability. And the same beta naught plus beta 1 times of x should be a very, very big positive number. Only then I will get a higher probability. Right? In the same fashion, if I'll just go back here, guys, we are saying I am more confident that one of the data point is more of class 2 the moment he is very, very far away from the hyperplane, and I'm very less confident if the same data point is closer to the hyperplane. Right? So we're saying the data point should be very far away. I should create a hyperplane in such a fashion that these people are all pretty far away over here. So what we are going to do is, guys, we are going to be creating a hyperplane. So the hyperplane's equation will go something like this. Okay, it will be W transpose X plus B, pretty much the same thing what you saw in a neural network model. And then we are saying this guy is going to give us what is called as a distance. Okay, this W and B will basically design the hyperplane. When you give this X as an input, it will give you the distance. Distance, or also called as margin. What do you mean by margin? Let's say if this is a data point, right? If I want to know how much far is he from the hyperplane, that is what is called as margin, or the distance. I can calculate the distance or the margin by doing W transpose X plus B. Okay. So what are we doing? We are saying I will go back and create a classifier or an SVM model which goes like this. H of X is equal to W transpose X plus B, where X will be the input, W and B will be the coefficients that we are going to estimate, and X will be the input, right, as we just spoke. The moment we push in all the numbers, he should tell us what is the margin of each and every data point from this particular hyperplane that we have just created. Say for an example, if I have a data point here, we have some weights and biases with which we would have created this particular hyperplane. Now you have an X input. What is X input? He has certain value of age, certain value of BMI probably. You push in the value. Now he's going to tell us, hey, my margin, okay, I'll just call it as margin for now. My margin is probably positive 2 units. Similarly, let us assume this is a data point. We are going to pass his inputs. He is going to tell us, I am having a margin which is equal to minus 2 units because I am on the left hand side right now. He says, hey, I am on the right hand side, hence is positive 2 units. Hey, this guy says I'm on the left hand side, hence I'm going to have minus 2 units. So the more and more the margin, the more and more happier we are, right? In fact, this is not the right definition of margin, guys. Now we're going to say, so the people on the right hand side are having a positive distance, people on the left hand side are having a negative distance. It kind of confuses me. That's what he is saying. Hence, what he's going to do is, instead of using target values of zeros and ones, guys, he will convert it as target values of -1 and +1. Okay. Instead of keeping it as 0 and 1, he'll convert it as -1 and +1. And now he will go back and find the margin, which is what we call as a functional margin, which is equal to yi times w transpose xi plus b. So what are we doing? We are basically computing something called as functional margin, or the distance of a data point from an hyperplane. The functional margin formula goes like this. Gamma cap of I is equal to yi times w transpose xi plus b. Okay. So let me go again, guys. So let's go to OneNote. So what we are saying is, we are saying, hey, I have two predictors, x1 here and x2 here. I'm plotting a lot of data points, and we are coming up with. So this is one data point. Probably this is another data point. We need to find the perpendicular distance between the data point and the hyperplane, because that's going to be the the shortest distance, right? We need to find what is this distance. So what our SVM model is saying is, he's saying you can find the distance of people by using this formula. He's saying, I'm going to create a classifier like this. It goes with this equation. H of x with respect to the weights and biases we have constructed is equal to W transpose x plus b. So he's saying it's a function which is W transpose x plus b. So he's saying this is the classifier we have created. So what is this? This is basically the classifier we have created. Now when you want to compute the distance of any data point to this particular classifier, he says it's very simple. Just go back and substitute the x value, you will get the distance. So if I substitute this guy's x value, he will tell me that the distance is positive 2 units. If I substitute this guy, he will tell us minus 2 units. But when we want to solve the problem, guys, we want to keep the distances positive. You can't say, hey, it's at a positive 2 distance, it's at a negative 2 distance. You can't have it like this. You need to keep it all as positive distances only. That's why we are saying, I have target value of 0 and 1. But I will assume target values to become -1 and +1. Why? Because for a data point who's having 1 as the target, if you are telling me W transpose x plus b is positive 2 units, when I multiply it, yi times W transpose x plus b, positive answer, I still end up with a positive answer here. So we're saying what? I still end up with a positive margin. While for a data point like this guy who's having target value of -1, if I come up with a distance which is -2 units, when I multiply these people, I would still end up with a positive result here. That is the reason why, guys, we are saying I can help you calculate the distance of each and every data point from the hyperplane using this formula, which we call as functional margin. What is functional margin? Functional margin is given by this formula. It's given as gamma cap of I. Okay. So what is I? Basically any data point. So I'll say a given data point will have a xi and a yi. So what is xi? It's some data point, x1, his suitable target y1. x2 is some data point, his suitable target y2. So for any data point, if you would like to calculate what is the margin or what is the distance, he says just do gamma cap of I is equal to, tell me what is the target of that particular guy multiplied by the weights times your xi plus b. That's all. He's saying what? Take up the target value take up the predictor value and push it to the equation, which is weight times xi plus b multiplied with yi. This will give you what is called as a functional margin, or otherwise it will give you what is the distance of each and every data point from the hyperplane that we have. Why are we calculating the hyperplane? Because we just discussed we want each and every data point to be very, very far away as much as possible. So what are we going to do? We are going to go back and tell, hey, SVM model, I want you to estimate this weights and biases in such a fashion that every data point is very, very far away. That's all. This is exactly what an SVM model is going to do. That's all. This is everything that you need to understand about an SVM model. Let me just reiterate. So we had logistic regression. In logistic regression, what did we say? We said for a target value of 1, we are saying theta transpose x should be a very, very big positive number. Only then you'll get a higher probability, because for target value of 1, higher probability is good. For a target value of 0, theta transpose x should be a very, very big negative number. Only then you'll get a lesser probability, because a less probability is good for a target value of 0. In the same fashion, here we are saying, hey, I want the data points to be very, very far away, which means the W transpose x plus b, right, should be a very, very, very big positive number for a target value of 1, and the same W transpose x plus b should be a very, very, very big negative number for a target value of -1. So it should be what? It should be a very, very big positive number for a target value of 1, and should be a very, very big negative number for a target value of -1. But during the optimization, you can't really handle positives and negatives. It's going to be a problem. You all remember in linear regression, we did errors were negative and errors were positive. So how do we handle it? We did a square. In the same fashion, here we are saying to keep the net margin positive, let us multiply by the target value, shall we? So I'm getting a big positive 2 for a target value of 1. Both of them are positive. End result is positive. I have a target value which is -1. I'm getting a margin of -2. I'll get a positive 2 margin right now. Right? So I'm getting a positive margin all the time. So I'll get distances to be always positive. There are cases where it can be negative also, which means it's a misclassification. So the guy's target is 1, but you are predicting it is -2. It is a misclassification, right? When you multiply, you'll get -2. Similarly, you're saying the guy's target is -1, you're predicting +2. This is also a problem for me. These cases are misclassification cases. So what we are doing is, guys, we are basically saying, hey, the margin for each and every data point will be a positive result, okay, provided they are correct, okay, provided they are correct when you multiply yi times W transpose xi plus b. This particular margin you need to keep increasing as much as possible. This is exactly what a support vector machine model is going to do for us. That's all, guys. So what are we saying? We are saying the objective is nothing but please maximize the functional margin for each and every data point. What is the definition of a functional margin? We are saying, hey, theoretically using formulas, if you find yi times W transpose x plus b should give you a higher distance is what he's telling us. This is what is called as a functional margin here. We want each and every data point to be as far as much as possible from the hyperplane. Only then I can give more and more confident predictions is what he's saying. Now tell me, guys, till this particular are you all probably confident? I mean, I would say following on the same page. What is functional margin? Why did we write a formula like this? yi times W transpose x plus b. Why should it be maximum? Why should it be bigger and bigger? Do you all agree till here? Yeah. Okay. So let's go over again. So we were basically talking about something called as functional margin. So there are basically two kinds of margin that we're going to be discussing today. The first one is called functional margin. The second one will be called as a geometric margin. Okay. There are two kinds of margins that we're going to be discussing today. Now what we have is we have something called functional margin that we're discussing. Even when you talk about SVM model, right, there are two kinds of SVM models you can create. One is called a hard margin SVM, and another guy is called a soft margin SVM. So what is the first case? The first case is a hard margin SVM, and the second case is basically a soft margin SVM. And how can I compute the margins? There are two types of margins you can do. One is something called functional margin. The second one is something called geometric margin. So what is a functional margin? We just discussed it. Functional margin given as gamma cap of I. Why is it the I? Because for each and every data point, I want to calculate how far are they. So you can see here, right? So we have a lot of data points. For each and every data point, I want to calculate what is the gamma of I. Okay. So here it's given as R. It's coming to geometric margin. So let's look at this. Okay. So each and every data point, I want to calculate how far are they. This is gamma cap of 1. This is gamma cap of 2, gamma cap of 3, gamma cap of 4, gamma cap of 5, 6, 7, 8, 9, 10, 11. So I want to calculate the distance of each and every data point from their hyperplane that we are creating, which is given as take up the true value of that data point and multiply it with W transpose Xi plus B. So what is the intuition behind this particular formula? We are saying W and B is nothing but the coefficients that our model is going to come up with, which is a linear hyperplane. X is an input that we are going to pass. Based on the true value target, he will go back and estimate what should be the W and B, which will give you the maximum functional margin as much as possible. That is, each and every data point should be as far as much as possible from these guys. This is exactly what we are saying. Okay. Or in fact, a better way of doing it, guys, what we typically do is, instead of looking at all the margins, right? So what you will do is you will initially compute this guy's margin, this guy, 3rd, 4, 5, 6, 7, 8, 9, 10, 11. You will calculate all their margins, okay? Out of all the 11 people, you will find who is the most minimum, who is the closest to the hyperplane. So you're saying, give me the gamma cap of I, where you keep checking for I running from 1 till n. Whoever is having the least value, right, that will become my ultimate functional margin. So what are we saying? We are saying I want the ultimate functional margin. It will be a single value, okay? I don't think I can keep maximizing everybody. So if you compare with the linear regression, everybody had an error. I can't keep minimizing each and every error right now, but rather I can work on a single result, which is cumulative error or average error. That's why here we are saying every data point's margin cannot be constantly looked at. Rather, give me the data point who's most closest towards hyperplane. That is, he's having the least margin. This guy, I will take it up. I will call this guy as the functional margin. And this guy, I will try to maximize as much as possible. So I won't be working with everybody. I'll work with the guy who's most closest towards the hyperplane. That guy I will try to maximize is what the functional margin is actually speaking, telling us. Okay. So this is one extra addition, guys. We are basically finding the margin for every data point, but we won't be maximizing it for every data point. If I maximize it for the most closest guy to the hyperplane, that in turn will basically make all the other people pretty far away from him. So the most closest guy is exactly what he should be worried about. Whoever is most closest, he will be monitored and he will be maximized right now. This is basically the definition of a functional margin, which all of us we know it, we just discussed. One problem there with this functional margin is that, guys, you can easily get a higher functional margin by doing a very simple mathematical hack. So what can you do? You can do a very simple mathematical hack and you can increase this particular distances. So say for an example, if you just go back here, okay? So let us assume that this is a hyperplane that you've created, okay? So what we are coming up with, we are coming up with a weight vector. So just keep in mind, guys, that the decision boundary you're creating and the weight vector you're creating will be orthogonal to each other. They will be at 90 degrees to each other. Which means the weight vector you're computing, guys, if you find another person who is at orthogonal to this guy, you are basically finding who is your hyperplane. So you are computing weight vector. If you compute weight vector, then just find who is at 90 degrees to this guy. He will become your decision boundary. That's all. So the blue color line is the decision boundary. The red color arrow that you see is the weight vector. What happens is, guys, you know that vectors have what? Magnitude and direction. They have what? They have magnitude and direction. So just because you want a higher margin, what I can do is I can do a small mathematical hack. What is a mathematical hack? Instead of keeping it as plain W vector, I can probably make it as 2 times of W vector. So even if I make it as 2 times of W vector, my decision boundary is still in the same position only. Who is orthogonal to 2 times of W vector is the same decision boundary. Or I will make it as 3 times of weight vector. But the decision boundary is still in the same location only, right? So what is actually happening is, guys, here to get a fake answer, that is to get a fake functional margin and probably cheat somebody, what you can do is you can take up the weights and biases and probably make it as 2 times of weights and 2 times of biases. You'll end up with a functional margin which is pretty big. All you're doing is you're keeping the direction as it is. Only the magnitude of the vector is getting bigger and bigger. That's all. We can just easily cheat with this kind of a mathematical hack. Because you're finding the distance, I can easily cheat the distance by just coming up with a very high weight vector and a very high bias value. That's all. But that is not what we wanted. I don't want a weight vector who is dependent on magnitude. No. The weight vector that we're coming up with, right? It should not be magnitude dependent. I am more worried only about the direction. Why? Because you can give me a weight vector going this direction. That will give me a decision boundary like this. You can give me a weight vector in this direction. That will give me a decision boundary like this. A weight vector in this direction, which will give me a decision boundary like this. So I am not worried about the magnitude. I am more worried about the direction. I want to know the direction only, please. I don't want the magnitude. Hence, what we're going to do is, guys, now comes a solution for us who's going to solve the problem. So the second guy, geometric margin, is saying, hey, don't worry. The functional margin was cheating you, right? He said gamma kappa phi will be what? Yi times W transpose Xi plus P. Where by changing the weights and biases to a bigger value, you'll end up with a bigger functional margin, right? So this is what your functional margin was telling. Geometric margin is saying, don't worry, we can just normalize it. He's saying, let's divide it by the weight vector. Let's normalize it. So he's saying, I will give you something called as geometric margin, which is equal to the functional margin divided by the norm of the weight vector. Basically, you're saying the formula will become yi times w transpose xi plus b divided by the norm of your weight vector. So you're saying, let's not use functional margin anymore. Rather, let us start using geometric margin, where the geometric margin is solving this particular solution. He's saying functional margins can easily be cheated by keeping a higher magnitude of weight vector, but the direction is still the same. You still end up with the same decision boundary. So what we will do is we'll normalize it by the weight vector. So the weight vector is always the unit vector only, but I will still end up with the same direction and I can create my decision boundary right now. So this is the point, guys. So we are saying, hey, functional margin, you can cheat it by having different magnitudes of weights and biases, but the geometric margin, it need not be so. Just normalize it, and then you can still end up with the proper margin value right now. He's saying this is the actual distance of each and every data point from your original hyperplane. The previous distance can be cheated easily by keeping 2 times of weight vector, 5 times of weight vector, 20 times of weight vector. Here he's saying you can't do it. Even if you're going to do it, he will basically scale it down. He will make it as a unit vector is what geometric margin is telling us. He's saying, I want the proper geometric distance, okay? You can't cheat me like what like what functional margin was telling us. Now the same concept. Now we are saying, hey, I can't be maximizing each and every geometric margin. Rather, let me go back and find who is having the least geometric margin out of all the people. That will become my geometric margin finally, which I will try to maximize as much as possible. So he's saying what? Hey, for each and every data point, you can compute geometric margin. So I don't think I can go back and maximize each and every person. That's a headache for me. Rather, what I will do is I'll just find who is the most closest to the hyperplane, and only that particular guy I will try to maximize as much as possible. This is exactly what the SVM predictive model is going to do for us. He's saying, hey, I will try to maximize the geometric margin for the point who's most closest towards the hyperplane. What is SVM saying? SVM is saying, I'm going to increase geometric margin. I'm going to increase what? Geometric margin for the point most closest to our hyperplane we have created. Okay. So he's not using functional margin because that can be easily, what I would say is cheated, right? You can kind of come up with the cheat, what I would say is, kind of a duplicate number, some kind of a wrong number, right? And then you're not going to maximize it for every data point that you see here, but rather just do it for the point who's most closest towards the hyperplane. Or otherwise, in our words, we call it as extremities. People who are most closest, you call it as extremities. The extreme people of a given class. So the most closest person to the hyperplane will be the right person. He'll be monitoring to increase this geometric margin here. Okay. So this is exactly what an SVM is going to do, guys. So as we just discussed, right, the SVM has the capability of creating any kind of hyperplane that he wants. So he can create something like this, he can create something like this. But what is a good boundary? A good boundary is somebody who's very far away from the, extremities. So this is one extreme. This is another extreme. They're very far away. The delta and delta is pretty big. But here in this fashion, he becomes an extremity, he becomes an extremity, but now this delta and delta is very small. So we are saying the delta has to be maximum, or otherwise the margins will have to be bigger, which you are computing using a geometric margin given as gamma of I is equal to y of I times W transpose xi plus b divided by the weight vector. I can't be maximizing it for every person. So let us find who's having the least geometric margin. That particular guy, we will try to maximize as much as possible. So out of all the geometric margin, out of all the data points, right, calculate who's the most closest towards him or who's having the least geometric margin. That guy we will try to maximize as much as possible. So if I push him, I need to push him. I need to push these guys also. Eventually you're pushing everybody. So just be worried about the closest people. If those people are separated properly, it means everybody else have got separated properly. This is exactly what our SVM model here is going to do for us. Right? Following till here, guys, do you all agree with me on this parts of what is the functional margin, what is the geometric margin? Yes or no? Do you all follow this one? What are functional margins? What are geometric margins? What are they actually calculating? Distances. Why do we have to maximize? I'm just getting 3 answers. How about others? Savik, Ravi, Nizam, are you guys convinced? Okay. Okay. Okay, cool. So let's do something. Okay, so let's probably take a 10-minute break, shall we? Right? So let's take a 10 minutes break, guys. So let's be back at 7:10. So what we've just got introduced is to the margins. Now I'll tell you how the optimization is going to work. Okay, so how the SCM model will go back and estimate the weights and biases. Let's look at some Excel examples also on how he's going to achieve it. Okay, so this is what we're going to be discussing. So let's come back probably after 10 minutes. We'll go to the next half of our session. Okay.
This conference will now be recorded.
So I think there's going to be a little bit of noise because it's raining cats and dogs here. So I'm pretty sure people in Bangalore should be seeing it. So it's like almost literally every weekend we say here in Bangalore that it's actually raining pretty heavily. So it's nice to see also. Okay, so great. So, and by the way, guys, if there's any disconnectivity in the internet, please just give me a couple of minutes. I'll just probably, connect through a different network. Okay, so. Okay. Oh, last Saturday your flight got delayed. Exactly. Yeah. I think literally like last week for past 5-6 days continuously every evening it was actually raining very heavily. There was a heavy downpour. So last Saturday it got delayed. Lucky that it didn't get cancelled. So at least it got delayed. Okay. Cool. So I think then probably let's get started. Yeah, so let's get started. So the next couple of things that we're going to discuss, guys, is actually speaking, I would say a little bit too much. Why? Because it's all about optimization. He's basically going to go back and do some optimizations, for which there's a lot of steps that he's going to follow. I think it's a little out of scope for us. We don't have to discuss much in detail, but I'll give you a very plain overview of it. Okay, what exactly is he actually trying to do? So we just discussed, right? We just discussed saying that, we have two kinds of margins. Originally, people came up with something called as functional margin. It's more of a theoretical nature, more of a formula nature, where we can just go back and find some weights and biases. We'll have some inputs. The moment we supply it, it's going to give us what is called as margins, right? And we said that this is actually a small problem. The reason because it can be easily kind of duplicated. Not duplicate is not the right word, but probably kind of cheated by just having some weights and biases scaled up by a couple of units up, or scaling it by a couple of times up. So that's why we came up with something called geometric margin, where we said, hey, I'm going to normalize it with the weight vector. So the moment I normalize it, even if you're going to try to grow up so much, it may not happen because always that guy is going to pull it down to become as a unit vector. So increasing geometric margin is what we need to do here, correct? Guys, now I want you all to understand two other keywords, something called as hard margin, and then we also have something called as soft margin. So what is a hard margin problem? A hard margin problem is a case where this SVM is going to create his hyperplane in such a fashion that literally no misclassifications are happening. So what is a hard margin? The hard margin problem is a case where, guys, he is very hard on his constraints, which means, he's kind of, very strict on the constraints. The constraints are that he says, I'm going to be creating a linear hyperplane and make sure that I'm not making even a single misclassification. Which means when I create a hyperplane like this and I say here it is class 1 and here it is probably class 2, there may not be a member of class 1 available here or a member of class 2 to be available here. So he's saying I may not make any such misclassification. I'm going to somehow make sure that everybody is kind of getting separated out in the right manner. So this is what is called as a hard margin SVM. So what is the point? We're saying, hey, I'm not going to allow any misclassification. I'm very perfect. That's why it's called as a hard margin SVM. But now suppose in case, guys, we are given a data set something like this. Let's take this case where it's actually not possible to create a linear SVM. Okay, so you can't probably create a linear SVM. It needs to probably take a small curve or something like this. You may not be able to create a linear SVM here. These are the cases where you will create something called as a soft margin SVM. What is this? This is called as a soft margin SVM, typically created on a non-linearly separable data. What is this soft margin SVM actually doing? He is saying, unlike what the hard margin was doing, I am not so hard on my constraints. I might create a linear hyperplane by allowing some misclassifications to happen. So what is he saying? He is saying, unlike somebody like a hard margin SVM, right? I'm not so hard on my constraint. I'm not very strict on it. I'm probably going to create a hyperplane which may allow certain misclassifications also to happen. So which means going back here, if this is the data that we had, right? If you wanted to create a hard margin SVM and make sure that nobody has got misclassified, you might have created a plane something like this. You might probably end up creating a plane something like this. But it doesn't look good, right? Because you can see that the distances are all very negligible. It's very small. But rather saying it's okay for this particular point to be misclassified. And now if I create a hyperplane like this, I get pretty much good distance here, isn't it? So what are we saying? We are saying, I think you're very, very hard on your constraint and you're trying to not misclassify this guy, at the cost of which you'll end up creating an SVM something like this, which may have a very small amount of margin. Let's not do like that. Let's say it's okay to make a misclassification on this guy. So we'll just forget that there is even a point somebody like this. Let's release him out. Now with the rest of the people, we can create a hyperplane like this and make sure that there are good margins for each and every data point here. So this is exactly what is called as a soft margin SVM. What are we doing in a hard margin? In a hard margin, we are saying the hyperplane will be created in such a fashion that there are no misclassifications that's going to happen. But in a soft margin SVM, it's not so. He says it's okay. I will create hyperplane in such a fashion that there can be misclassifications which will be allowed. Because for non-linear data, for very nonlinear data, hard margin may not be able to be created. It's probably going to fail. It'll give us some random solution. It may not be possible to create a hard margin. So you need to relax on your constraints, saying it's okay to make a misclassification. Thereby, you can create something called a soft margin SVM here. So now if you guys ask me a question on how is this happening, how do you think we are creating a soft margin SVM, or how are we creating a hard margin SVM? Let's start a discussion with hard margin first. So the discussion first you're going to have is about hard margin. So we are saying, hey, the objective is to basically maximize geometric margin with respect to the weights and biases. That is, please try to find what is the weights and biases which will give us a high geometric margin, subjected to the constraint that each and every data point that we have used in our calculation. So what are we saying? Subjected to the constraint that each and every data point that we have used in the calculation is surely having their respective geometric margin greater than the most minimal one. So what are we doing, guys? We are saying gamma of I is equal to y of I times W transpose X of I plus B, right? This is geometric margin. And then what did we say? We said, hey, I don't think I can maximize by observing everybody. Rather, let us just find who is having the least distance. So we said, ultimately geometric margin is somebody who is having the most minimal geometric margin. So we are saying, whoever is having the most minimal geometric margin, that guy alone I will observe. So now we are saying, hey, for that particular point, right, the guy who is having the least geometric margin, probably he's having 2 units, try to maximize it, make it like 10 units, 20 units, 30 units, whatever it is, by finding what should be the weights and biases which will give you such a margin. But please make sure that every individual margin that you're finding, you can see here, every individual margin that you're finding is surely above the most minimal margin that you see here. So what are you saying? Literally every data point should be correctly predicted. We're saying all the data points should be correctly predicted. We don't want even a single data point to be misclassified. We're saying all the data points should be correctly predicted. And then we are also adding another constraint saying, hey boss, when I find the norm of the weight vector, it should be equal to 1. That is, the weight vector cannot grow as how he thinks. Suddenly he cannot make it as 2 magnitude or 5 magnitudes or 10 magnitudes. It's not allowed. The magnitude should be equal to 1. So this is also another constraint that we are adding. So we are saying, hey, maximize the geometric margin, which is nothing but the data point who is most closest towards the hyperplane. That is the guy who is having the least geometric margin. That guy we should maximize, provided every other data point is surely above this minimal threshold that we have kept. Also make sure that you are not cheating me by giving a weight vector which is very big magnitude. Make sure that the magnitude of the weight vector is equal to 1. All of these things, we are basically baking it into one single statement here. Maximize the least guy's geometric margin, making sure that all the data points is surely having geometric margin greater than the least one. And also please make sure that the weight vector's magnitude is equal to 1. You can't give me a weight vector, who's probably working with, his own magnitudes. You can't be 2, 3, 4, 10 and all. It has to be equal to 1. This is exactly what is a hard margin SVM's objective function. So if somebody is asking us, hey, what is the objective function for a hard margin SVM? This is exactly what you need to present it to them. Tell them geometric margin for the least guy should be maximized. keeping in mind that for every data point is surely above this particular value and the weight vector is equal to 1. This is exactly what we're going to do. But there are another series of steps that we will be doing here, guys. Okay, basically to solve this objective equation to make it much more simpler. Okay, I'm not very sure if I need to jump into all those steps. But okay, let's do it. So let's do it. So I'll just give you a very brief overview. So this is what we have, right? The objective function. I'm pretty sure till here everybody should have followed. Now what we are saying is, we are saying keeping two constraints. This is one constraint, this is another constraint. This constraint is a very hectic constraint, okay? Many of your optimizers may not be able to solve. That is why we are going to bake this constraint inside this objective itself. We will say maximize geometric margin of this particular format. That is nothing but functional margin by norm of weight vector. So this is geometric margin, right? Gamma is geometric margin, which is equal to functional margin by weight vector. So instead of handling it separately, we are saying include it in your equation like this. So gamma cap divided by norm of weight vector. So he will handle it. Second constraint is handled. Subjected to constraint that yi times w transpose x plus b should be greater than or equal to the minimal functional margin that we are computing. For every data point should be correctly predicted. Then what we are doing is, guys, we are saying, okay, let us assume that functional margin needs to be at least equal to 1. It's an assumption that they will make. So it should be at least equal to 1. That is why we are saying maximize 1 by weight vector subjected to the constraint that each and every data point is surely having at least one geometric margin unit. Okay, so when I say gamma cap of 1, it's functional, right? Which is otherwise nothing but geometric also. Okay, you're basically trying to equate them here by this method. So you're saying, you know, it should be at least greater than 1. Then the next step is, guys, having 1 by weight vector is not very easy to solve. That's why we will always keep 1 by weight vector square. So squares are much more easier to solve. So, you know, your equations will, you know, be easier. So it might become a curve like this, but W might have been something like this. So keeping it a square will be much more easier. So that's why we are squaring it. Then we are saying, instead of doing a maximization operation, let's do a minimization operation. So that's why we are saying minimize plain weight vector square subjected to the constraint that yi times w transpose xi times b should be greater than or equal to 1, because typically there are no maximum implementations, but Python and all has minimum implementations. There are optimizers which will solve minimum problem. There are no optimizations which can solve maximum problem. So converting a max into a min is nothing but doing an inverse. So we are saying minimize weight vector square. But suppose in case you're going to differentiate something. So let's say you're going to differentiate x square. You will get what? You'll get 2x. So this 2 to get cancelled, we will just assume a 1 by 2 here. So if you differentiate, what will happen? It will become 2 times of weight into 1 by 2. This 2 and this 2 will get cancelled. So that's why they're keeping a denominator of 1 by 2. So this becomes our final objective equation, guys. So the final objective equation is what? It is minimizing 1 by 2 times of your weight vector square subjected to the constraint that yi times w transpose xi plus b should be greater than or equal to positive 1. Isn't it a little too much, right? So that's why I didn't get into the details here. It's a little too much. It's more of mathematical in nature, something that we need not worry about. Okay. So what we had was maximizing geometric margin, making sure that everybody is greater than this geometric margin with weight vector equal to 1. But keeping this as a separate constraint is a problem. That's why we're including it here. We know that geometric is equal to functional by weight vector. Now subjected to the constraint that every data point should be greater than the functional margin. Then we are assuming let function margin be equal to 1. Hence the equation becomes like this. Then we are saying, hey, weight vector maximizing is the problem. Let's make it as weight vector square, which is much more easier. So it becomes maximizing 1 by weight vector square subjected to this constraint. Then we are saying instead of maximization, let's do a minimization. So it will become plain weight vector square subjected to constraint. Then we are saying, hey, this square after I differentiate will give me a 2. So to cancel that 2 and this 2, we are basically including a 1 by 2 fraction here. So this 1 by 2, and after differentiating that 2, they will cancel out. So it is minimizing 1 by 2 times of your weight vector square subjected to the constraint that yi times w transpose xi plus b should be greater than or equal to positive 1. So this is going to be our final objective equation here. Just take a note of this one. So this is exactly what you need to understand. So the first step and the last step, minimizing 1 by 2 times of a weight vector square subjected to the constraint that yi times w transpose xi plus b is greater than or equal to positive 1. This is exactly the objective equation we have at hand. Okay. So let's go to the PPT. I have the same thing in the PPT also. So you guys can see here. Do I have it somewhere here? Looks like I don't have it. Okay. So you can see here. So we are saying, please minimize 1 by 2 times your weight vector square subjected to the constraint that each and every person should be greater than or equal to positive 1. This becomes what is called as your hard margin SVM here. So let's try to create the hard margin SVM. So let's go back here. I have a data set with me. Okay. So look at this data set, guys. We have two predictors, x1 and x2. What are these two guys? They're basically our predictors. This is the target we have, which is yi. So these two people are basically the predictors, and this is the target we have. How many data points do we have? We have 12 data points. Each and every data points, x1 and x2 value is here. We have created a scatter plot here. You guys can see it. So now what I'm going to do is, guys, let's go back to our equation. We said this is our objective, correct? So let me just come down here. Let's paste it. This is the objective. Okay. So this is our objective equation. We are saying minimize 1 by 2 times of a weight vector square subjected to the constraint that each and every person is having margin greater than 1 at least. So let's go back and compute this one, shall we? Let's compute for some value of weight and biases what's happening. So I'll assume weight 1 and 1, bias also as 1. So let's go back and compute yi times w transpose x plus b. So we are saying, hey, this is equal to matrix multiplication between x transpose w or w transpose x, doesn't make much of a difference. Okay, so the weight matrix has to be made as constant. So we are doing w transpose x plus b, plus the b is what? The bias that you can see here. So what do you guys see? It's a matrix multiplication between your x and w, adding it with the bias. This should give us all the respective margins, right? So let me assume -1, -2, and 3, or probably 10 to. So some of these ways, if I would get a negative answer, I'll be happy. So -5, -6, -4. No, okay. Anyways, so what you can actually see is that you'll typically get margins which are positive and negative, right? When you're doing W transpose X plus B. Because for people on the right hand side, you'll have positive margins. People on the left hand side, you'll have negative margins. Oh, I think these are all negative. You can see here, guys. Yes, they are negative. So let's format it a little different. Go to format cells, number. The other format is not there with bracket. Okay, anyways, this is negative, guys. So this positive 7 is positive, but this is negative 7. Okay, so positive 7 and negative 7 you're getting. So he's saying I'm on the right hand side at positive 7 units. I'm on the left hand side with positive 7 units. Now we are saying, hey, this is a little confusing. So I would like to multiply u by yi. So we are saying, let's multiply it to the yi. Now I will get everybody to be positive in nature. Okay. So you can see these guys have all become positive, but these guys are negative. Why? Because they are still misclassifications. They are misclassifications. That's why here we are adding a constraint saying everybody should be greater than 1. There shouldn't be any misclassifications. You can see here, guys. These people are all negatives, isn't it? Minus 13, minus 3, minus 23. They have got correctly classified, but their distance is on the left-hand side. That's why minus. Now when we go here and we make it as multiply it with yi, you will now understand which of these people have got correctly classified, which of these guys did not get. Okay, so you can see. So these 4 or 5 people, they are getting minus answer because they've got misclassified. They're all misclassifications. That's why you're going to add a constraint saying they should be greater than 1. They should not get misclassified. So now what we will do is, let's implement the constraint in a minute. Okay. Let us go back and compute the previous term 1 by 2 weight vector square. So I'll just go back and say, hey, this is equal to 1 by 2 times, or otherwise 0.5 times matrix multiplication between the weight and weight itself. So we'll say, hey, transpose the weight and multiply it with the same weight itself. Okay. So this will give us what is called as weight vector square. I'll just scale it up by 1000 units so that it becomes a proper number we can display. Control Shift Enter. He is giving us a functional margin of, no, sorry, it's not functional margin. It is 1 by 2 times weight vector square of 10,000 or something. So what has happened? We have basically found 1 by 2 times of your weight vector square. Weight vector, you have multiplied them, so become square. 1 by 2 here. As the what? As the 1 by 2 times weight vector square value. Now what we will do is, guys, we'll go to data, we'll go to solver, let's reset all. Now we will say he is the objective whom you need to try to minimize by changing the values of the weights and biases that we see here. So what are we doing? We are saying, hey, he is the objective which you need to try to minimize by changing the weights and biases, subjected to the constraint that all the margins are greater than or equal to 1. So what are we saying? They should be greater than or equal to 1. So we are saying each and every margin should be greater than or equal to 1. This is unconstrained variable and all. It doesn't make any sense here. So you can just unpick it. So let's go over again. Minimize 1 by 2 times of your weight vector square, subject to the constraint that yi times w transpose xi plus b should be greater than or equal to plus 1, which means you're saying do not allow any misclassifications here. Now let us hit solve, and he is given us a solution. Let's hit OK. He is telling us that, boss, weight vector of 0.33, 0.33 and a bias value of minus 5.66 will give you the least 1 by 2 times of your weight vector square, which is 111. And he'll also make sure that each and every data point are getting correctly classified right now. Can you see? All the people have got correctly classified right now, isn't it? There are no misclassifications at all. Everybody have got correctly classified. That's a good thing for us, which means we were able to create the hard margin properly right now. We were able to solve what? The hard margin problem right now properly. So these are the weights we have assumed. This is the bias that we came up with. We computed yi times w transpose xi plus p, which is nothing but the margin. Then we said each and every margin should be very much greater than or equal to 1, and make sure that 1 by 2 times of a weight vector square is minimized. Now after doing this, you can see that all the people have got correctly classified. There are no people with negative answers. Only if it is a negative answer, it means it's on the wrong side, right? So target value of 1, which should have been on the right hand side, is probably on the left hand side with minus distance. Or target value of -1, which should have been on the left hand side, is probably on the right hand side with a positive distance. Because there is nobody negative, which means you have created a very good hard margin problem right now. Now you guys might ask me a question. How can we visualize the hyperplane? We have got the weight vectors, right? 0.33, 0.33. Can you please tell me how to visualize the hyperplane? This might be a question you guys will ask me. My answer is very simple. So what we are actually doing is, we said, hey, I want you to create my hyperplane. This is the center black line you see. And then we said, I want to make sure that every data point is having distance greater than 1. So at least 1 unit far away they should be, is what you're saying. So the dotted lines that you see, right, is the 1 unit line that we're talking about. Which means, guys, the centermost hyperplane is nothing but W transpose x plus b is equal to 0. That is, data points on the hyperplane should give you what? Distance equal to 0. Data points on this point should give you what? W transpose x plus b is equal to positive 1. Data points sitting on this particular line should give you a distance what? W transpose x plus b is equal to -1. Agree on that? W transpose x plus b is the distance. If there is any data point sitting on the hyperplane, then the distance from the hyperplane is equal to 0. If the data point is here, then the distance from the hyperplane is positive 1. If the data point is here, then the distance from the hyperplane is equal to -1. What do we need? We need the center hyperplane, which is W transpose x plus b is equal to 0. We want the two thresholds also. Why? Because we kept a constraint that every data point should be at least 1 unit far away. So we need the center solid line and the two dotted lines. So the way you can do this is simple. We are saying W transpose x plus b. How many W's and how many X and how many B's do we have? W1 X1 plus W2 X2 plus bias. This is what we have. So if you want to understand the hyperplane, you just have to assume data points who are sitting at 0, at a distance of 0. We are saying if I could find data points sitting at a distance of 0, then I can trace out the hyperplane. Now what we're going to do is, guys, let's go to the Excel. We'll assume some value of x1 right now. I'm assuming what values? I'm assuming 0, I'm assuming 1, I'm assuming 2, 3, 4, 5, 6 goes on till 16. If this is my x1, we need to find what should be the x2 right now, which will give us points on the hyperplane. So let's do that. We are saying I have weight. I have x1. I need to find x2 right now. Basically, you're tracing the line. So 0.33 times x1 plus 0.33 times x2 minus 5.667 is equal to 0. Then now you can say 0.33 x2 is equal to minus 0.33 x1 plus 5.667. And 3 x1 plus 5.667 divided by 0.33. Or otherwise, let's keep this aside. Without substituting numbers, shall we do it? We are saying W2x2 is equal to minus W1x1 minus B. X2 is equal to minus W1x1 minus B divided by W2. This is the formula we have. Now all we need to do is, we have the weights already, we have the biases already, we just need to assume some X values and you can trace out their X2 values. Let's go back and do that here. So formula, this is equal to what? Minus W1 into X1. So we are saying minus of W1 into X1. So this is one single term. I'll keep it in bracket. Minus of what? B. B is over here. I hope everybody agrees. Minus of W1 into X1 minus of B. This is my numerator. I will divide it by the denominator. What is the denominator? W2, which is this particular guy. So I have to make which people constant? C4 needs to be made as constant because it's a weight. C6, this guy needs to be made as constant. C5 is also constant. Let's hit enter. If you have 0 as a value, it should have been 17. This data point will be on the hyperplane. Similarly, let's do it for the second guy. Let's do it for the third guy. Let's do it literally for everyone. Now on the right hand side, you can see you've got your hyperplane right now. So all you're doing is, guys, you have the weights and biases. You're just assuming one of the feature and you are cooking up what should be the other feature. That's all. You're assuming one guy, substituting in the formula, and you're getting the other feature as an output. That's all. Now you're able to create your hyperplane. In the same fashions, you can create the other two people. I'll tell you what is the formula. Basically, the bias should get incremented. That's all. I think C6 is your bias, right? Make it as +1 and hit Control Enter. And similarly, make it as -1 and hit Control Enter. That's all. You'll get the other two lines that you wanted. So just go back and do the formula. Just make it as 1. No, you will see. Here there'll be a 1, here there'll be a 1, or there'll be a -1 and a -1. So we're just saying, hey, the bias needs to be subtracted by 1 or added with 1, which will give us the other two lines right now. So the centermost blue line is your hyperplane, guys. The other two black lines that you see is a threshold. What do you mean by threshold? Because we said every data point should surely have functional margin greater than 1. They should surely be above 1, right? This is the threshold we kept. So we are saying this black lines are nothing but the lines which are having value equal to 1. The margins equal to 1. So the centermost blue line is your hyperplane. The right hand side and the left hand side are basically the threshold lines that we are talking about. So this is exactly how you create a hard margin SVM here. We assume some values of weights and biases, or shall we go again one more time? Let's solve it. So we'll assume some value of weight and biases, 1, 1 and 1 probably. We need to compute the constraint. We're saying, hey, it's a matrix multiplication between the X value and the weight value. Then please add it with the bias value. This will help me understand what is the margin. There will be positive margins and negative margins, right? People on the right hand side will give you positive distance. People on the left hand side will give you negative distance. But while I'm calculating distance, you can't tell me I travel minus 200 kilometers. You have to tell me that I traveled in that direction, but it was 200 kilometers in magnitude. So direction was different. That's why we are saying, hey, if you multiply it with your yi, now you will give me the right distance. You will give me all positive distances. In spite of doing it, there are negative distances, which means what? I should have traveled in the northern direction, but I traveled in the southward direction by 15 kilometers. Or I should have gone in the south by 20 kilometers. Wrong things I've done, right? Wrong directions I've traveled. That is why now we are saying, hey, please make sure that next time I don't travel in the wrong direction. Please make sure that the distance is greater than +1. At least +1, at least in the right direction. Let me go by 1 kilometer now. So even if I'm not doing 15 kilometers in the north direction, at least let me go by 1 kilometer. So that's why we are saying, hey, the constraint is going to be distances should be greater than +1. What is the objective? 1 by 2 times weight vector square. This is equal to 0.5 because it's 1 by 2 times matrix multiplication between transpose of your W, comma the W itself, right? I'll just scale it up by 1000 units so that it looks like a decent number. Okay, so Control Shift Enter, it gives us 1000 right now. So it is what? 0.5, which is 1 by 2 times matrix multiplication between weight and weight itself, which will give you weight square, times the 1000. It's a simple scalar with which I maximized. Data, solver, reset all, okay. Who's the objective? 1 by 2 times weight vector square. Minimize or maximize? Minimize. By changing whom? Weights and biases. Is there any constraint? Yes, it is. Every data point should surely get correctly classified by one distance at least. They should get correctly classified with one distance at least. Unconstrained variables, should they be non-negative? Not really. They can go for negative also. Let's hit solve. Let's hit OK. You've got 0.33, 0.33 and minus 5.67. You can ask him to solve again. You may get a better solution. You can go once again, ask him to solve. You may get a better solution. So you can do it many number of times also, guys, to get a better solution all the time. So this is the weights and biases that we have. Now what are we saying? We're saying if you take up any SVM model, the blue line will be the hyperplane. The other dotted blue lines will be the threshold lines. Let us assume there is some data point on the hyperplane. If I calculate the margin for this guy, what should be the distance? It should be equal to 0 because the distance of the data point and the hyperplane is equal to 0. How do you calculate margins? You do W transpose X plus B. That is why we are saying for any person on the hyperplane, W transpose X plus B will be 0. Any person on the right hand side, right? If you calculate W transpose X plus B, it should be equal to 1. This threshold is what? Any person on the left hand side should give you W transpose X plus B is equal to -1. So here it's +1, here it's -1, here it's 0. Using this property, we can go back and trace out the line that we want. So you wanted to calculate the hyperplane, which is W transpose X plus B equal to 0. We have 2 weights and 2 predictors, 1 bias equal to 0. Assume X1, you have already found W and B. You just need to find what is X2. So X2 is nothing but minus W1 X1 minus B divided by W2. This will give you hyperplane line. The other threshold lines will be what? W1 X1 plus W2 X2 plus B is equal to 1. So formula will become W2 X2 is equal to 1 minus B minus W1 X1. Then X2 will become divided by W2. Here the formula will become X2 is equal to -1 minus B minus W1 X1 divided by W2, where you're keeping W transpose X plus B is equal to -1. Here W transpose X plus B is equal to +1. So these are the 3 formulas that we need to implement. So assume some value of X1, use the weights and biases we have already found. You can trace out the 3 individual lines is what we are saying. How to do that? Go to Excel. Here now we are saying this is equal to, what is the formula? Minus of W1 into X1. So minus of W1 into X1. X1 we have assumed. Minus of B divided by W2. This is what we have. Okay, so this is the formula. All we need to do is make sure that you're making the weights and the biases all constant while you're dragging it down. Let's hit enter. He gives you 17. Let's apply it everywhere. You'll get your center hyperplane. I'll copy the same formula. We'll just go down here. For bias alone, we'll make it as +1. Apply it. Let's go here. For bias alone, we'll make it as -1 and we'll apply it completely. Hence, you are able to trace your hyperplane and the two respective the thresholds or the decision boundaries. So blue line is the hyperplane. The other two black lines are your decision boundaries. You can call them as the decision boundaries right now. So this is the methodology of creating a hard margin SVM, guys. Basically a case where you don't allow any of the data points to be misclassified. See here, all the positives got correctly classified. All the negatives got correctly classified. Not a single data point will be misclassified here. So that's the work of a support vector machine's hard margin version. It's hard margin. It's called as hard because it's trying so hard to not make any misclassifications. Hence, it's called a hard margin problem. Okay. Tell me, guys, are you all comfortable till here? Yes or no? I don't think for the last 45 minutes I asked this question, but do you guys feel comfortable with all these things that we have just done? Should be simple, right? So once you know the objective function, then solving it should have been very simple. It's just that how did you end up with the objective function would have been a headache. Okay. Looks good? Okay. How about for others? Nizam? Yatendra looks good. Manohar is okay. Okay. Great. I think it has been a little too much, right? A lot of concepts that we have discussed today. So great. So I think we'll probably call it a day with this. Okay. So thank you guys. Thanks for joining. So please let me know if there's any questions, else we can call today. Yeah. I'll upload all the files and all the videos probably by tomorrow afternoon or evening. Okay. Great. Thank you. Thanks, guys.